A very good morning to my fellow examiners. My name is Tong Lin from 4 SCSB, session 2021-2022, semester 2. My PSM title is Support Vector Machine Recursive Feature Elimination SVM-RFE for feature selection of multiomics data of lung cancer. I am supervised by Dr. Azura. Without further ado, please let me start my presentation. This is the content of my presentation. Firstly, I will briefly go through the introduction of the study, which includes the problem statement, research aim, objectives, and scope. In Chapter 2, I will go through some of my findings from previous papers, which includes the multiomics integration approaches, feature selection methods and benefits, and the type of encoders. Chapter 3 covers the research framework, data set, and performance measure. In Chapter 4, I will go through the experimental design, which covers several phases such as data preprocessing, multiomics integration, feature selection, SMOT, and classification. Chapter 5 will contain the result and discussion obtained from Chapter 4, which are the outputs of SVM-RFE and the performance of SDAE and VAE in classification. In Chapter 6, I will summarize the research achievements, constraints, and future works to improve the research. Let's start with Chapter 1, Introduction. Let's start off with lung cancer. Lung cancer is among the deadliest cancer in the world. In 2018, it contributed about 11.6% of total cancer cases and caused around 1.8 million deaths. Even with advanced treatment, the prognosis for lung cancer is still not very optimistic. However, recent researchers found out that AI technologies such as the machine learning and deep learning could help bring improvement to the existing prognosis procedure. In this research, the dataset used is an multiomics data. But first, what is an omics? So omics is an disciplinary field in biology. There are several types of omics such as the genomics, epigenomics, transcriptomics, and more. Omics data are considered as big data because they fulfill the properties of a big data. Multiomics refers to the combination of two or more omics. According to researchers, multiomics analysis could help elicit more insights about biological data. It allows a more holistic study in biological phenomena which helps assist in cancer prognosis. Moving on to the problem background, it is mostly concerned about the multiomics data. Multiomics analysis have many benefits, but it is very challenging to implement. Since multiomics covers multiple omics fields, there are massive amounts of data to process. Typically, there are three main challenges in multiomics analysis, which are the curse of dimensionality, or also known as the large P and small m problem. Large P refers to the large number of features, while small m refers to the small number of samples. Scaling and sampling bias is another challenge, as for different omics types, there are different sampling techniques and the extracted raw data are also at different scale. One omics expression might have more features than the other omics expression. Besides that, an effective integration method is also needed to combine the different single omics data into one multi-omics data. The technique used to combine the omics data need to be effective, or otherwise the combined multi-omics data might not give any new insights at all. In this study, I focus on the large dimensionality problem. When the dimensionality of the data is large, it tends to cause inefficient or inappropriate learning of the models since there are too many features to be learned. Since there are too many features, the researchers would try to discard some features which are thought to be less relevant among the tens of thousands of features. But the problem is we usually do not know which feature to keep or discard without a proper model. Therefore, there is a need of implementing an efficient feature selection method to produce optimal results from classification. The research aims to employ the feature selection of multiomics data by selecting the highest rank of features that contribute to promising relationship with the output class using SVM-RFE. The research objectives are as follows. RO1 is to study and understand the algorithm of SVM-RFE, SDAE, and VAE models. RO2 is to determine the suitable parameters to be used in developing the SVM-RFE, SDAE, and VAE models and apply appropriate fine-tuning methods to them. RO3 is to validate and verify the performance of SVM-RFE feature selection model using SDAE and VAE models based on the selected performance measures. The research scope is as follows. The study restricts the multiomics study to 3 omics types, which are the genomics or gene expression, epigenomics or DNA methylation, and transcriptomics or mRNA expression. The data is obtained from this following link. Next, we will discuss the literature review. For literature review, we will first look at the different approaches of multiomics integration. There are 3 types of approaches as shown in the table, along with their description and advantages. Model-based integration approach builds a predictive model for each omics type and combines all the models together to form a final model. The advantage of this approach is that it allows the data type to be collected from different sets of patients with the same phenotype. Concatenation-based integration is another approach that directly concatenates the features of columns from each omics type to produce a large matrix. This approach is straightforward and is simple to implement, which is the reason why the study chose this method for integration. Transformation-based integration approach transforms the omics data into intermediate kernel or graph form, and then the intermediate forms are combined to form a large matrix. For feature selection, there are also 3 methods. The filter method is simple and fast, and it can scale from low to high dimensionality and is independent of a classifier. But due to it being independent to a classifier, it lacks the information related to the interaction between the data and the classifier. This causes the feature dependencies to be ignored and hence the least effective method among the 3 methods. The wrapper method solves the weaknesses in the filter method by involving the use of a classifier to cater feature dependencies. It is thought to be the most effective method among the 3. However, it suffers from disadvantages such as being computationally expensive, slow, and has the risk of overfitting. The SVM-RFE method used in this study belongs to the wrapper method. The embedded method is a hybrid of the filter and wrapper method. It combines the benefits of both methods, and it has a less chance of overfitting and less computationally expensive, but is still less effective than the wrapper method. There are several benefits from performing feature selection on the dataset. Firstly, it facilitates data visualization and data comprehensibility. By reducing the size of the dataset, it helps in reducing the storage requirement. Smaller datasets also mean faster training time and help us to escape the curse of dimensionality. By eliminating the curse of dimensionality, the models can now produce better predictive performance and higher computational efficiency. This slide compares the difference between the 2 autoencoders that is used in this study, the stack denoising autoencoder SDAE and the variational autoencoder VAE. Both the models are a variant of a generic autoencoder. They have 3 primary layers, which are the input, hidden, and output layers. SDAE is formed when we stack several DAE together. Noise is introduced to the model to force the autoencoder to learn the important features of the data to reconstruct the original input with minimal loss. SDAE is not generative. It only tries to reconstruct the given input with the least error. VAE, on the other hand, uses latent distribution and a sampler to generate new data points. The data points are encoded into the latent distribution to create a probabilistic model. The sampler then creates new data points from the latent distribution with minimal reconstruction loss. Therefore, VAE is generative. This chapter covers the methodology used to conduct the experiment. The research framework is divided based on the research objectives. For RO1, it involves the literature review and acquiring data. RO2 mainly covers the implementation part of the research. It has 4 parts, which are data preprocessing, multiomics integration, feature selection algorithm development, and deep learning classifier algorithm development. RO3 will compile the results obtained and discuss on the findings. The details of Part A is as follows. Firstly, literature review is done. Then, from the review, the methodology of implementing the algorithms are chosen. After that, the data is acquired. Part B involves the data preprocessing. The flow of pre-processing starts with identifying missing value and data imputation to handle the missing values. After data imputation, the data is normalized to perform variance threshold analysis. Part C is the multiomics integration part. It involves the concatenation of the 3 omics data into one single multiomics data. After that, the data is split into train, validation, and test set. The feature selection algorithm, which is SVM-RFE, is developed in Part D. The output from SVM-RFE is then used in Part E for classification. In Part E, the feature selected data first undergo class balancing to produce equal amount of samples between the positive and negative outcomes. Then, the SDAE and VAE models are developed separately. Part F covers the result analysis and discussion. The outputs obtained from SVM-RFE, SDAE, and VAE are discussed. The performance of SDAE and VAE are also compared against each other. The raw dataset downloaded from the website contains 4 different files, which are the 3 omics data and 1 clinical data. The 3 omics data include gene expression or genomics, DNA methylation or epigenomics, and miRNA expression or transcriptomics. The clinical data, on the other hand, contains many other informations about the patients, but the main concern are the patient ID and the class label of whether or not the patient has lung cancer. This is a summary of the raw dataset obtained. The number of rows and columns are displayed in the table at the top. The 3 omics data appears to have many samples as shown in the number of rows, but this is actually misleading because the row and columns are actually inverted. This will be discussed in the next few slides. From the clinical data, we can see that there are about 500 patients with cancer and 120 without cancer. These are the performance measures that will be used in the study to assess the model. By plotting the confusion matrix, more measurements can be calculated, such as the accuracy, precision, recall, and F1 score. Next, we will look at the implementation of the experiment. The experimental workflow is very similar to the research framework. First, data is obtained and undergo pre-processing. After cleaning the data integration is performed to create the multiomics data. The multiomics data then undergo feature selection using SVM-RFE to obtain the most optimal feature subsets. The optimal feature subsets are then fed to the deep learning models for classification. The results obtained from the SVM-RFE, SDAE, and VAE algorithms are then discussed at the end of the research. Starting with data acquisition, the datasets are obtained and their initial data shape is tabulated in the table. Despite claiming that the datasets were pre-processed and cleaned, it is found out that there are still some flaws in the dataset. Therefore, the pre-processing steps as follows are executed. Firstly, the data transposition is performed on a raw omics dataset to fix the inverted rows and columns problem. Then, data imputation involves checking for duplicated and missing values and replace them appropriately. Data and normalization follows after finishing the data imputation. The normalized omics data then undergo variance threshold analysis, which checks for and removes zero variance features. As mentioned previously, the raw omics data came with inverted rows and columns. In the raw omics data, the rows represent the omics expression, while the columns represent the samples. To proceed with the experiment, the data transposition is required. As shown in the figure at the top left corner, the raw dataset has the rows as omics expression, while the column as samples. After performing data transposition as shown in the bottom right corner, the omics data now have proper data structure in which the rows now represent the samples, while the columns represents the omics expression. In data imputation, it was found out that there is no duplicated data or missing values. However, it is noticed that some samples have same values for the mean, and max value when the omics data are inspected. This means that there are some columns that have zero variance features that do not contribute to classification. This problem will be handled during the zero variance analysis step after the data normalization step. In order to perform zero variance analysis, the omics data need to be normalized first. All 3 omics data are normalized so that the values are between 1 and 0. As mentioned previously, the variance threshold analysis or the VT analysis is carried out to check and remove the zero variance features. From the analysis, it is found out that there are 287 and 160 zero variance features from gene expression and mRNA expression respectively. The DNA methylation expression data does not contain any zero variance features. These zero variance features are then removed. This is a summary of the data preprocessing step. Starting with the raw data, the rows and columns are inverted. After data transposition, the row and column now represent the samples and omics features respectively. In VT analysis, about 200 features from both gene expression and miRNA expression omics data are removed. Before going further, the class label distribution for each omics data are inspected. It is noticed that all three omics data have about 90% of the samples having primary tumor class, which is the positive class indicating the patients having cancer, and 10% of the samples having solid tissue normal class, which is the negative class indicating the patients have no cancer or are healthy. This shows some degree of class imbalance, which is part of the nature of the omics dataset. The pre-processing step for the clinical data is pretty straightforward. The two only important features are the sample ID and sample type. These two features are extracted as the ID is required for multi-omics integration and the sample type feature represents the sample's class label. In multi-omics integration phase, the three omics data and one clinical data are concatenated together to form a multi-omics data. After multi-omics integration, the data undergoes data splitting. As mentioned previously, the study integrates the multi-omics data using concatenation-based integration approach, which is concatenating all the columns from the three omics data and one clinical data together. The concatenation is performed based on the ID column. This is a summary of the multi-omics integration phase. At the end of the multi-omics integration phase, the final data now contains 344 rows with about 26,000 features. The class distribution of the integrated multi-omics data is inspected. It is noticed that class imbalance problem became more serious as now out of 344 samples, the positive class now have 341 samples while only 3 samples for the negative class. This translates into roughly a 99:1 ratio, indicating the dataset is now severely imbalanced. The integrated multi-omics data undergoes data splitting. There are two types of splitting performed onto the multi-omics data. For feature selection, the multi-omics data is split into 70% train and 30% test set. The train set then is used for two-fold CV. For classification, the multi-omics data is similarly split into 70% train and 30% test set. However, the train set is split again into 70% train and 30% validation set. Since the original integrated multi-omics data is already severely imbalanced, the train and test set after splitting is also imbalanced. It can be seen that there are only 2 negative samples in the train set and only 1 negative sample in the test set. The multi-omics train set is used for feature selection using SVM-RFE. The objective of feature selection in this experiment is to extract 20 feature subsets with different number of features. For each selected subset, grid search is used to find the most optimal set of hyperparameter for the SVM-RFE. Two-fold CV is performed on each selected feature subset to obtain initial insight about each of the feature subset. From the CV result, the mean and standard deviation for accuracy for each feature subset can be determined. Besides that, the computation time is also taken note. Finally, the omics composition or distribution is recorded to check for the behavior of the SVM-RFE in eliminating features from each omics in each feature subset. As mentioned previously, grid search is used to find the most optimal hyperparameter for the SVM-RFE in selecting each feature subset. C is set to 0.1, 1, 10 and 100. It represents the penalty of the error term. It controls the trade-off between misclassification and the smoothness of the hyperplane of the SVM model. The SVM kernel is set to linear as it is the only kernel that produces feature importance or feature coefficient that is necessary for the SVM-RFE to eliminate features via ranking. Step refers to the number of features to remove per iteration in RFE, and it is set to 1, 2 and 3. This image illustrates the workflow of SVM-RFE. The raw multi-omics data, which contains about 26,000 of features, are fed into the SVM-RFE algorithm. In the first iteration, SVM-RFE removes about 6,000 features from the raw data and outputs a feature subset with 20,000 features. These feature subsets with 20,000 features is kept and named as FS20,000. In the second iteration, SVM-RFE continues to remove features from FS20,000. From this iteration onwards, SVM-RFE will eliminate 1,000 features in each iteration. Therefore, at the end of this iteration, 1,000 features will be removed and the output will be FS19,000. This process continues until SVM-RFE has removed enough features to reach FS1000. At the end, 20 feature subsets with a difference of 1,000 features from each other are produced. After feature selection, the experiment proceeds with classification. In classification, two deep learning models, which are SDAE and VAE, are built. Unfortunately, due to hardware constraint, only 5 smallest feature subsets selected from the feature selection phase are used for classification. More details on that later. Before building the classification model, SMOT is performed on the train set of the 5 feature subsets for class balancing. SMOT refers to the synthetic minority oversampling technique. SMOT is used to synthetically generate new samples from the minority class, which is solid tissue normal, in each feature subset. The goal of SMOT is to match the number of samples in the minority class to the majority class. The table shows the hyperparameter of SMOT algorithm. Sampling strategy is set to 1 as in 100% of the number of samples in the majority class, meaning that in the end, the number of samples in both classes will be the same. K-neighbors is unfortunately forced to set to 1 as the value of K-neighbors has to be smaller than the number of samples in the minority class. In this case, the number of minority class in the train set is only 2. Random state is set so that the result can be repeatable. This diagram shows the class distribution of the train set before and after SMOT. After SMOT, the number of samples in both classes are now the same. This image shows the finalized class label distribution for the train and test set. Since the train set has undergone SMOT, both classes are now equal. On the other hand, the test set is still severely imbalanced. Moving on, we have the model construction methods for SDAE and VAE. The model building for both the classifiers are slightly different. During unsupervised learning, both the models are trained using the standard autoencoder structure, which has the encoder, the latent layer, and the decoder components. In supervised learning, the unsupervised SDAE model is fine-tuned into a supervised learning model by replacing the decoder part with a new layer with only one node with sigma activation function. This acts as the new output layer for the SDAE model. For VAE model, the sample data by the sampler are extracted, and then an external classifier, or in this case an SVM model, is used to classify the sample data. The reason behind using the external classifier for the VAE model will be discussed later. This is the neural network for SDAE during unsupervised learning phase. There are 3 layers in the encoder, 1 layer for the latent layer, and 3 layers for the decoder. Noise is first introduced at the first layer. The dimension of the layers in the encoder is decreased by 30% for each subsequent layer. The latent layer is now 10 times smaller than the original input at only 10%. This allows the SDAE model to learn only the important features in the latent layer for reconstruction. On the other hand, the dimension of the layers in the decoder is increased by 30% for each subsequent layer. At the last layer of the decoder, or the output layer, the dimension is returned to 100% to reconstruct the input. As for the activation function, all layers are using redo except for the output layer, which has sigma activation function. The hyperparameter used for the SDAE unsupervised learning is shown. As mentioned previously, the dimension of the layers in the encoder part decreases by 30% for each subsequent layers and vice versa for the decoder part. The grey italic text shows an example of the dimension of the layers if S5000 is used as the input. The epoch and batch size used are 50 and 16 respectively, with Adam as the optimizer. The activation function is the same as the ones mentioned previously. For the loss function, binary cross entropy is used as the classification involves a binary classification. The Gaussian noise dropout rate is set to 10%. For supervised learning, the unsupervised SDAE model is fine-tuned by replacing the decoder part with a layer with only one node with sigmoid function. This allows the SDAE model to output value between 0 and 1, in which 0 represents the negative class while 1 represents the positive class. The hyperparameters used for the supervised SDAE model is the same as in unsupervised learning. The only difference is the layers of the model. This is the neural network for the unsupervised learning of the VAE model. The neural network structure is generally the same as the SDAE model, except there is no noise introduced to the model and the VAE model contains an extra layer of sampler. The hyperparameters used for the VAE unsupervised learning is also very similar to the one in SDAE. The only exceptions are the activation functions and the loss function. The sampler of the VAE model uses linear activation function. Two loss functions are used for the VAE model, the generative loss and KL loss. These two loss functions are used since they are specific to the VAE model. The image shows the structure of the supervised VAE model. The sampled data points stored in the latent layer by the sampler are extracted and fed into the SVM model for classification. Since an external SVM is used for the classification, the hyperparameters for it has to be specified. The hyperparameter for the SVM model is kept as default, which is with C of 1.0 and linear kernel. Next, we will look at the result obtained from the experiment and some discussion on the result. First, we look at the result of SVM-RFE. This is the grid search result for the SVM-RFE. Apparently, the grid search decided that all feature subsets could use the same set of optimal hyperparameter of C equals to 0.1 and step equals to 1. This is the mean and standard deviation of the CV result for each feature subset shown in box plot. It can be seen that from FS 20,000 to FS 14,000, the mean accuracy is 0.996. On the other hand, FS 13,000 to FS 1,000 has mean accuracy of 1.0. This is the computation time for the selection of each feature subset. The SVM-RFE algorithm ran for a total of 3 hours and 9 minutes to select 20 feature subsets. It can be seen that for every 1,000 lesser features, the computation time speeds up by about 30 seconds. This chart shows the omics composition for each feature subset after SVM-RFE. Generally, it can be seen that the composition of gene expression declines from FS 20,000 to 5,000, while the composition of DNA methylation rises. The opposite trend is observed from FS 4,000 to 1,000 as the composition of gene expression rises while the DNA methylation declines. mRNA expression composition, on the other hand, fluctuates and declines slowly. This is the discussion for the result of SVM-RFE. For the CV result, it can be said that when the feature subset becomes smaller, more low predictive power features are removed. This means that the remaining features are now more correlated with the class label, so the classifier can more consistently distinguish between the classes for better performance. For the omics composition, when the number of features are larger, most of the gene expression features have low predictive power. Conversely, the DNA methylation features are more relevant to the class label, which is why they are kept by the SVM-RFE. On the other hand, when the number of features become lesser, most of the gene expression features with low predictive powers have been removed. Conversely, the DNA methylation features are now less relevant to the class label, hence removed by the SVM-RFE. mRNA expression, on the other hand, seems to have little influence in class prediction, as the other two omics expressions have much more features. Moving on, we will look at the result from the SDAE model. Figure shows the model loss for the unsupervised SDAE model for FS 1000 to 5000. All of them produce small loss, which is a good sign. It is noticed that smaller feature subset produces smaller loss. This is the accuracy of the supervised SDAE model on the test set. It can be seen that the lowest observed accuracy is 0.99, which is very high. On the other hand, only FS 1000 and 4000 achieved 100% accuracy. When looking at the confusion matrix, it can be seen that FS2000, 3000 and 5000 have one false positive. This means that they have misclassified the only negative class while correctly classifying the positive classes, leading to an accuracy of 99%. For the SDAE discussion, all the models built with different feature subsets seems to have excellent performance based on the accuracy score. However, accuracy is actually misleading when taking the class label distribution of the test set into consideration. The test set has 103 positive instances and only one negative instance. The model can achieve very high accuracy even by predicting only the majority class, which is 0.9904. The rest of the metrics, such as the precision, recall, and F1 score, are not very helpful either. AUC score is the only metric that provides useful information. The AUC scores for SDAE models built with FS2000, 3000 and 5000 are 0.5, showing zero prediction capability since they are always misclassifying the one and only negative instance. Next, we will look at the VAE results. Starting with the VAE unsupervised learning model loss, it is observed that the model loss is able to converge. Smaller feature subsets also produce smaller model loss. This image shows the visualization of the sample data points using two randomly selected features. It can be seen that the VAE model is able to sample data points which has clear separation between classes. The reason of using an external classifier such as an SVM for the VAE model is because the accuracy obtained from the supervised VAE model, which is fine-tuned using the same method as the SDAE model, show very weird accuracy. All accuracy fluctuated at 50% for all feature subsets. This is the confusion matrix obtained from the external SVM classifier on the sample data. It can be seen that all models achieve 100% accuracy. This is the discussion for VAE model. The result obtained from the fine-tuned supervised learning model is odd, as all the models built with different feature subsets produce accuracies that fluctuate at 50%. When looking at the sample data, there is a clear separation between the instances with different class label. Therefore, the odd result obtained from the fine-tuned VAE model could not be explained. All the models built with different feature subsets achieve perfect score when using an external model to classify the sample data by the sampler in the VAE model. This result is accurate and it is in line with the separation of the data points between different class labels. The table shows the side-by-side comparison between the scores for each metric for both SDAE and VAE for 5 feature subsets. It can be seen that only FS1000 and 4000 are the only two feature subsets that perform equally well on both SDAE and VAE models. According to the comparison of the metrics between the SDAE and VAE models, it can be seen that only 2 out of 5 SDAE models, which is the FS1000 and 4000s, are able to correctly classify all the instances, while all 5 VAE models are able to do so. On this specific multiomics data, the VAE models are more capable of classifying the data points compared to the SDAE models. Since FS1000 and 4000 are the two feature subsets that perform equally well on both the SDAE and VAE models, the study concludes that FS1000 and 4000 are the two most optimal feature subsets selected by the SVM RFE algorithm. Moving on to the conclusion, the research achievement, constraints, and future works will be discussed. This is the achievement of the study. For RO1, the study managed to identify the underlying logic for the algorithms of SVM RFE, SDAE, and VAE. For RO2, the study managed to determine the most optimal set of hyperparameters for the SVM algorithm using grid search. The unsupervised learning SDAE and VAE models are also successfully fine-tuned into supervised learning model capable of classification. For RO3, the study managed to explain the results obtained from the SVM RFE, SDAE, and VAE algorithms based on the selected performance measures. Next, I will explain the research constraints. The first research constraint is the severely imbalanced multiomics dataset. The integrated multiomics dataset consists of 344 instances with 341 positive and 3 negative outcomes. After trend test split, the trend set consists of 238 positive and 2 negative outcomes while the test set has 103 and 1 respectively. Oversampling techniques such as mod could be used to generate more samples for the train set. The test set, however, is still severely imbalanced. The second constraint is hardware constraint. The GPU offered by the Google Colab does not have sufficient memory. When building the deep learning model using FS2 20000, nearly a billion of parameters are required as shown in the bottom left image. Building the neural network alone consumed almost 100% of the GPU's memory as shown in the bottom right image, causing the rest of the experiment to halt. There are a few future works suggested for future researchers. These suggestions are mostly to solve the research constraints mentioned previously. Firstly, using a new and latest multi-omics dataset is able to solve the severely imbalanced dataset issue, as new datasets should contain more samples. Next, by using a better GPU, the hardware constraint can be solved. This can be done either by using a workstation with better GPU with more memory, or by subscribing to Google Colab's premium plan that offers better GPU. That's all for my PSM2 presentation. I apologize for my mistakes throughout the video presentation. Thank you.